Welcome. In this first section of Chapter 6, we're just reviewing complex numbers, which we've learned before. Just to remind you, I represents the square root of -1, which we would normally consider not possible. But there are times when it is nice to be able to work with it even though it's not possible, and so mathematicians decided that it should be assigned the imaginary number, letter I, to represent that, so that we can just work with it like it's a variable. Because of that, when you take and square a number, if you were to square a square root, squaring a square root just cancels it out. So that would leave you with the -1 that's on the inside. So that's what I squared equals is -1. Notice how when we square the I, we no longer even have an imaginary number. This actually cycles through so that I cubed can be replaced with -I, because it's basically like I times I squared, and since I squared is -1, I cubed can be -I. And then I to the fourth is just I squared times I squared, which is -1 times a -1, which is a positive 1. So then if we keep going through this pattern, it'll just repeat through these four options, so that no matter what the exponent is on I, we can change it to something that either has no I at all, or just has a single I with no exponent. And so you'll never see I with an exponent in any simplified problems. You always want to get rid of any exponents on the i's. So like I said, this would repeat so that I to the fifth just equals I to the sixth equals -1, I to the seventh equals -I, and I to the eighth equals 1. So every time you have an exponent that's a multiple of 4, so it's divisible by 4, your answer will be 1. So for example, if I wanted you to simplify I to the 100th, that answer is simply 1, because 100 is divisible by 4, and therefore that's where it comes in the cycle. If we go to a different number, like, I don't know, 67, the closest multiple of 4 would be I to the 64th, and I to the third would be what we would have to multiply that by in order to have our 67. Well, this becomes 1 because it's a multiple of 4, and I to the third is represented by -I, and so no matter what the exponent is, we can always get rid of the I completely or get it down to an I without an exponent. Okay. So a complex number is called complex because it has a real part and an imaginary part. So A represents the real part of our complex number, and B represents the imaginary part. And of course this could be minus depending on, these are integers, so this could be negative, this could be negative. And notice how this is the standard form. So you always, when you're writing in standard form and you're simplifying, you put the real part first and then the imaginary part. And you always make sure you've gotten rid of any exponents higher than 1, like we just barely discussed. Okay. Now there's many operations you can do with complex numbers. The most simple is to add and subtract. Let's just go over some examples because it's basically just combining like terms. It's just like as if you have numbers with x's in them and you just treat the I like as if it's a variable, but it's not, because it's a fixed value that doesn't exist, of the square root of -1. But just like other variables, or even if we're working with a fixed number like pi, or square roots are this way too. When you're combining them, they have to be the same type of terms. Okay, so since this is plus, even though I've separated this complex number from this complex number, the parentheses don't really mean anything. We're just combining like terms. So -2 plus -4 is -6, and positive 3i plus a -9i would be -6i. So there would be If we subtract, we have to make sure that we distribute, or make sure that we remember that we're subtracting both of the terms in the binomial. So we have negative 1 minus a 3. Negative 1 minus 3 is negative 4, but don't forget you're also subtracting this. So negative 5i minus a negative 2i actually results in negative 5i plus 2i, which is a negative 3i. And see, in every case I've gotten this down to a standard form with our real and imaginary parts of each one, right? Okay. Multiply. So we can multiply complex numbers by foiling. So let's suppose we have 2 plus 3i and we're multiplying 5 minus 4i. Multiply 2 times 5 is 10. 2 times negative 4i would be negative 8i. 3i times 5 would be 15i, and then 3 times negative 4 would be negative 12i squared. Okay, well we want to get this back down to a standard form, so we don't want any squareds like this. Remember, an I squared simply equals negative 1. So this will turn this negative 12 into a positive 12. So now if we combine like terms, we have 10 plus 12 is 22. There's the real part of our answer. And then negative 8i plus 15i is positive 7i. And there's our complex number in standard form, even after multiplying. Okay, there's also division. If you were dividing two complex numbers, you would have something like 8 minus I over 2 plus I. So you're dividing two complex numbers, right? That's what that means. So in dividing two complex numbers, we still want it in this same standard form. Or another way to think of it is an I really is just a square root, and so we don't want that in the denominator, it's improper. So we want to simplify this. The best way to do that is by multiplying by the conjugate of the denominator. So we're going to use conjugates. So that's where you would multiply this by the conjugate, 2 minus I. But what you do to the bottom, you have to do to the top, so that you're multiplying by a common, well, you're multiplying by 1 because you have the same number on the top and the bottom, so it reduces to 1. And when you multiply something by 1, it doesn't change anything. When you multiply a fraction by 1, it changes the appearance, it doesn't change the value. Okay, so on the top we have 8 minus I and 2 minus I, so we have to FOIL those. So we would get 8 times 2 is 16, 8 times negative I is negative 8I, negative I times 2 would be negative 2I, and negative I times negative I would be positive I squared, but because it's an I squared, we can change that to a negative 1. Then in the denominator, we have 2 times 2. Here, I'm just going to rewrite it. Okay, so foiling this out, we would have 2 times 2 is 4, and then we would have 2 times negative I is negative 2I. I times 2 is positive 2I, and then I times negative I is negative I squared. So those two cancel each other out, which was the whole purpose of using a conjugate, because then this turns into a negative 1, and we completely get rid of that imaginary number in the denominator. Okay, so then we have 16 minus 1, because the I squared turned into a negative 1. So 16 minus 1 is 15. And then negative 8I minus 2I would be negative 10I. And 4 minus a negative 1, because the I squared turns into a negative 1, is 4 plus 1, which is 5. If this fraction was not reducible, I would write my final answer as a real minus an imaginary part, and it would be okay for it to just have fractions. But this is reducible, and so we're just going to get rid of the fractions. 15 divided by 5 is 3, and then we have a negative 2I here.
Teachers, please excuse this interruption. The students that were on the Utah Careers Day field trip, they're back. They should be coming to class now, so please watch for those kids. Thanks.
Okay, one last thing to talk about is simplifying problems. You'll be given like some ugly problems and just asked to simplify them. You will be tempted to distribute first. Don't distribute first. First, you must change your negatives to i's, because if you don't, then your answer actually will not end up being correct. So before we do anything else, we have to go through and change these two i's. So this negative becomes an I, and that is outside of the square root. So we have I square root 27 times square root of 9 minus I square root 2. So before I do anything else, another thing you might want to do right now is to go ahead and simplify these square roots if you can. Like 27 simplifies into 3 square root 3, and the square root of 9, of course, is just 3. So you could do that now or later. I would say do it now because 27 times 9 is kind of a big number that I don't want to think about. So I'm going to go ahead and simplify this. 27 is 9 times 3, so the square root of 9 is 3, and then I have a 3 left inside. So I would have 3i square root 3, and the square root of 9 is 3, and then I would have I square root 2. Okay, now I'm going to distribute. So 3i times 3 is 9i, and then we have the square root of 3, and then we have 3i times negative I, so negative 3i squared, and then we have a square root of 3 times the square root of 2, which is a square root of 6. This I squared turns into a negative 1, which turns our negative 3 into a positive 3. To put this in standard form, we put the real part first and the imaginary part second. So this is going to become our real part because of the I squared turning into negative 1. So I'm going to put that first in my answer. 3i squared, oh, the I squared's gone. Oops. 3 square root 6, because that turned that positive. And then this will just add on at the end 9i square root 3. So 3 square root 6, since that's kind of messy, I'll finish this, plus 9i square root 3 is the final answer because you've got your real part and your imaginary part. If you had started at the beginning and distributed first, this negative would have canceled out that negative, and so then you wouldn't have had an I squared that would have changed this sign. So if you hadn't distributed, you would have gotten a negative here, or maybe the negative would be here. Yeah, the negative would be here, which would be the incorrect answer. So it's important to always change your negative I or negative square roots to i's before you do any other algebraic simplifications that you know how to do. Alright, that should be it. Good luck.